In this video, we're going to learn about ways to combine capacitors in a circuit. There are two specific ways, kind of two simple ways of combining capacitors. We call them series and parallel. And first, we're going to start off talking about a parallel combination, which looks something like this. This would be three capacitors combined in parallel. And when capacitors are combined in parallel, it does not necessarily mean that the capacitors are literally parallel to each other, but rather it means that in any path going from the battery around the circuit and back to the battery, that you only pass through a single capacitor. So again, if I'm starting here, I could go through this first capacitor or through the second one or through this third one. And that's what helps me know that these are in parallel with each other. With each type of circuit that we study, we're going to talk about the rules for the voltage, otherwise known as potential difference, charge, and equivalent capacitance. Before we can actually talk about these, there's one very, very important rule that we use when we're studying any type of circuit, regardless of whether that circuit has resistors or capacitors or inductors, which is something we'll learn about in magnetism, or maybe a combination of all of those things. And that rule is known as the loop rule. It's one of Kirchhoff's laws. And the loop rule tells us that the net potential difference or the net voltage through any loop around your circuit must be zero. Okay, so what that means basically is that if I travel in any closed loop around my circuit, let's say I were to start here and travel around this way, my potential difference through that loop has to be zero. So let's think about what that means as we're talking about the voltage or potential difference across an individual capacitor. Let's look at that loop that I had outlined once more. It's a loop that was right here. So I start by going through the battery, and that has a positive potential difference because I'm going from negative to positive. So that's the potential difference of the battery. And then I go around here, and then I go through this capacitor. And the capacitor has a potential difference across it as well. We're assuming this capacitor is charged since it is connected to the battery. And you see that I'm going from the positive plate, where all my positive charges would collect, to the negative plate, where my negative charges would collect, and back around. And since I go from a positive potential to a negative potential, I would have a negative potential difference. And I'll call that delta V3 since the diagram calls that capacitor C3. And then I get back to where I started, so that's equal to 0. Because one number minus the other number equals 0, it tells me those two numbers must be equal to each other. I could do the exact same thing going through other loops. So starting down here, let's choose a different color here. Starting down here, going through the battery, but instead going through my second capacitor, getting back to where I started. This time, I'd have the positive potential difference going through the battery, and then once again, a negative potential difference, but this time it's the one across C2 equals 0. Well, that tells me that that potential difference across C2 must also be the same. And finally, I could do the exact same thing, but my loop could go through C1. And I'd find the same thing, that the potential difference across C1 must be equal to that potential difference across C2, which must be equal to the potential difference across C3, which must be equal to the potential difference across the battery. Again, this is all thanks to the loop rule, one of Kirchhoff's laws. Another thing that we know that charge is conserved. Okay, here's what that really means. That means we can't magically create charge and we can't destroy it. Because of that fact, the total charge in my circuit must be equal to the charge on each capacitor. Now, using those two facts, I can come up with an equation for what we call the equivalent capacitance. An equivalent capacitance means the capacitance that I would have if I were to take out all three of these capacitors and replace it with just a single one. So, to come up with that equation, I'm going to start out with my fact about charge, and I'm also going to use my equation that I know that is true for capacitance, which is that capacitance is charge divided by potential difference. Rearranging that equation tells me that charge is capacitance times potential difference. So the total charge would be equal to the total capacitance times the total potential difference. And charge 1 would be the first capacitor's capacitance times its potential difference. And then we have C2 times its potential difference plus C3 times its potential difference. Now notice that I didn't put any sort of subscripts on my delta V's, and that's because we know that they're all the exact same. And if I have things that are all the exact same in my equation, I can divide both sides of the equation by that value. And this lets me know that my equivalent capacitance can be calculated by the sum of the individual capacitors. On your equation sheet, this is written as Cp equals the sum of Ci. This is an equation that's on our equation sheet, so we're able to use it. But I wanted you to understand why that equation is true. We're going to go through the exact same concepts for series. In a series circuit, much like what you see here, rather than there being individual loops that you could travel around as you go around your circuit, in a series circuit, if you start at the battery, you must pass through all the resistors before returning to the battery. So this is just one example of a series circuit where I have three resistors that are in series. We are once again going to go through voltage, charge, and capacitance rules for each. We'll start off with voltage. Again, we're going to think about the loop rule. And let's say that I'm starting off in the bottom left corner of my circuit right here. And I'm traveling in a loop around my circuit. First thing I would encounter would be that battery. And I'm going from the negative side of the battery to the positive side of the battery. Right? And then the first thing I would do was I'd go through capacitor 1. And I'm going from the positive plate to the negative plate of that capacitor. So I'm going through a negative potential difference here. So minus delta V1. Once again, I do the same thing as I'm going through capacitor 2 from the positive plate to the negative plate. Minus delta V2. Same thing with C3, going from the positive plate to the negative plate. Minus delta V3 equals 0. Again, that was applying the loop rule, knowing that potential difference through any closed loop in a circuit must be equal to 0. I could also rearrange this equation that I've written here so that the voltage of the battery is equal to delta V1 plus delta V2 plus delta V3. So unlike last time where each capacitor was required to have the same potential difference, this time the potential differences all add up to being the potential difference of the battery. Now let's shift our focus onto charge. Let's think about how this charging process actually occurs this time. We know that capacitors get charged when we attach a battery to them. We have a single electron moving from the negative side of my battery. It gets energy from the battery, moves around the circuit, and then it gets stuck on this negative bottom plate of my capacitor 3. And because that charge got stuck there, that then would tell me that one of my negative charges on this top plate would move and get stuck here. And that would then repel one of my negative charges off the top plate of C2 and get stuck on this bottom plate of C1, which would then move a negative charge around the circuit. That negative charge would gain energy as it goes through the battery and would keep going. The process would keep going over and over again. Hopefully what you've noticed as we talked about this process, though, is that for every charge or every electron that accumulates on C3, we also get an electron accumulating on C2 and an electron accumulating on C1. That means that each of these would have to be the same. So what I'm saying here is that Q1 equals Q2, which equals Q3. Sometimes we also call that the total charge. Basically, this time when we have capacitors in series, they're each charged the same amount. So once again, we're going to look for an equivalent capacitance of this circuit as if I were to replace all of these capacitors with a single capacitor. And once again, to find an equation for that, I'm going to focus on my general capacitance equation, C equals Q over delta V. But this time, I'm going to solve this equation for delta V. Delta V would be equal to Q over C. And I'm going to plug that expression in for my general equation for voltage. That means that the delta V of the battery would be expressed as being the total charge divided by the total capacitance, or again, we call it equivalent capacitance, would be equal to delta V1, which would be Q1 over C1, plus delta V2, which is Q2 over C2, plus delta V3, or Q3 over C3. Now we know each one of these Q's is the exact same value, so I can cross them out this time. So in general, my equation here says that 1 over the equivalent capacitance in series is equal to the summation of 1 over Ci, I being whatever that integer value is for each capacitor. This is how it's written on your equation sheet. Even though we just went through the derivations for equivalent capacitance in series and in parallel, it's important that you know how we got there. But you are allowed to use those equations since they're on your equation sheet. What does not appear on your equation sheet are the voltage and charge rules for series and parallel circuits. Rather than focusing on memorizing these rules, my suggestion to you is to really focus on understanding why these rules are the case. Because as you know, the AP test is often written to work on checking your understanding rather than your memorization. To check your understanding after watching this video, I have a problem for you to do from your textbook. This is actually a combination of problems 67 and 68. We have two capacitors, one that's a 6 microfarad capacitor and one that's a 4 microfarad capacitor. And they're connected in series, and there's a potential difference of 200 volts applied across them. You could think of this as saying that they're connected to a 200 volt battery. Problem asks you to solve for 5 different quantities, things like equivalent capacitance and then charge and potential difference of each one. You'll then repeat the question as if those two same capacitors were connected in parallel. Do this problem and bring your answers with you to class, just so we can check and make sure you really understand these rules for series and parallel combinations of capacitors.